next presenter is Lucas Bindelli from Instituto Nacional del Agua, Argentina, with the presentation Hydrokinetic Energy Potential in Argentine Estuaries with High Tidal Ranges.
Thank you, Gonzalo. Hi, everybody. As Gonzalo said before, I'm from the National Water Institute, or ENA, as you can see there. And this is one of the few presentations that is not about waves. This is about tidal currents or hydrokinetic energy. And the idea of this presentation is to show you some the projects that we've been working on and some results and conclusions that we've obtained. We work in a team that handles numerical modeling, so we try to establish the amount of available energy and to characterize this energy into 5 different estuaries in southern Patagonia, Argentina. So to locate ourselves on the map, we have Argentina there, and this is the area of interest. And there we selected 5 estuaries, which are the Deseado, the Santa Cruz, the Coyle, the Gallegos, and the Grande. And the reason why we chose these estuaries is mainly because of these values here. So they all are either meso or macrotidal regime estuaries. And as you can see here, they have quite a big amplitude. So you can have an idea between the floor here and the roof. We've got about 7 meters maybe. So these here have a mean tidal range of 7-8 meters. So the difference between the highest and the lowest tides is about this high. And the interesting part is that sometimes they even reach about to 12 or even 13 meters, so twice as much as this height. So there's a lot of water going in and out of the estuaries. And if you have a look at the morphology in each case, they all have a small mouth. So we thought, okay, maybe this whole water going into these estuaries might have a flow that increases speed, maybe on the mouth. So this is something that we could have a look. And to do this, we decided to have an approach with numerical modeling and with a methodology known as nested models. So what we did is, first we did a rank 0 model that covers the entire Atlantic coast of Argentina, starting at the south of Brazil and going up to the south of Argentina. And we use the results of this model as boundary conditions of a smaller and more detailed model named rank 1. And if we do this a few times, so we do it here again, and a 4th time here, what we manage to do is we can bring the information from open seas up to the inside of the estuary, increasing detail and keeping computational costs limited. And the tools we used several different tools for this. So basically the software was Delft 3D, and then for the data we used bathymetric sources from the bathymetric charts. We also used satellite images to delimitate the coastal lines. And in cases where we didn't have all that information, we used global models. Then we had to assume some hypotheses because we didn't have much information. So we thought, okay, we are pretty certain that all these estuaries behave with astronomical tides. So that's the main forcing. We're not going to consider for now the meteorological tide. And we decided to simulate for a whole year just to have a good idea of how much energy in a mean value, in an average value along the whole year. To calibrate these models, since we were forcing with the astronomical tide, what we did is we took the predictions from the Argentine Hydrographic Service of astronomical tide, and we compared our results with those predictions. As you can see in this table, we've got some indicators, performance indicators, where we can see that there's a very good correlation in all cases, in all 5 estuaries. And the root mean square error might seem a little bit big, but if you consider that the big amplitudes that we have in these places, they actually fall within 5% of error, so it's considered acceptable. And you can see that actually about here. So the blue line is the predicted by the hydrographic service, and the red line is an output of one of the detailed models. And the main differences are about here at the peaks and at the valleys. But in the rest of the series, there's a good representation. Now, we calibrated those models, but we needed to validate them to make sure that we were representing properly the hydrodynamics. So we did two survey campaigns, one in 2018 and another one in 2022. So this one, what you can see here is just a summary of some results that we obtained on 2018. We took some measurements with ADCP for velocity. Here you can see the blue dots are the measurements, and the orange line is the model. So we can see that the model is underestimating a little bit the velocities that we have in part of the estuary. All of this is for the Santa Cruz River estuary, by the way. We only went to only one of these. And we also took the opportunity to do a bit of a test. So we took these floating devices, and we put some GPS trackers, and we put them to go with the flow. And then we measured their position in time, and we were able to obtain the distance and the position, but also the velocity that they reached at each point. So in this case, we go from white to red, from 0 to over 2 meters per second at the surface. And this is what you can see here, the comparison with the model. Again, the blue dots are the measurements, and the orange line is what the model predicted. So you can see in both cases there's a pretty good agreement with what we were representing and what we were measuring. The second campaign that we undertook was last year, in 2022. And having gathered a lot of information and processed all this, the results of these models, we thought, okay, maybe we need to be a bit more detailed on what we want to obtain. So the first thing that we did this time was we went to two of the estuaries, not just one, the Gallegos and the Santa Cruz. And first we measured the surface levels during 3 days that we spent in each estuary. And we were able to compare these measurements with the astronomical predictions of the hydrographic service. And even though these are small measurements in time, you can see that there's a very good approach between what we measured and the prediction of the hydrographic service. So this, in a way, validates the hypothesis, the initial hypothesis, even though it's only, at least for normal conditions. Maybe not, this is not the case for storm surges, but for regular conditions we can see a good match. And also we wanted to have a look at the 3D composition of the velocities on the estuaries. So this is just a sample so you can have a look. We go from 0 in blue up to 2.5 in red. 2.5 meters per second. So you can see that there's a big area that has about 2 meters per second in velocity, and about here in the surface there's a higher range of 2.5 meters per second. So these are the values, the velocity values that we find in these estuaries. Now, in case you haven't put much detail into how hydrokinetic energy works, this is a time series of the evolution of the velocity in one of the estuaries. Just as an example, this is the Santa Cruz. So you can see that there's peaks of, in this case, 2.5 meters per second, what we were seeing on the previous image. But there's also valleys that fall below 1 meter per second. So it's quite variable in time. That's why when we want to assess the energy available in these estuaries, what we try to do is to have a mean value that represents the entire time of a whole year. And why I'm showing the velocity every time is because there's an equation, this one here, that links the velocity of the flow with and the water density with the power density per square meter. So this is actually the indicator that we try to obtain to properly assess the available energy in an estuary. Using that equation, we can obtain for each of the 5 estuaries the results of mean power density, which is what I was showing before. And as you can see, all of 5 of them show values that are above 1 kilowatt per square meter. And as we'll see in a bit, that's a bit of a threshold to overpass. And in some cases, like Rio Gallegos, we have large areas that actually have a bit more, about 2.5 kilowatts per square meter. So these were very good indicators showing us that, okay, there's definitely some energy potential here that we need to keep on looking more into detail. But there's another important variable that we need to consider, which is minimum depths available. And this is because when we want to put a device in any of these estuaries, it's important that these devices remain underwater and so that they can work properly the entire time. And here you can see there's a very big variation in all cases. We can see in this, for example, we reach about 25, 30 meters, the same here in Santa Cruz. Deseado is a little bit shallower with depths of about 20 meters, but then Grande and Coyle are very, very shallow. So they only fall within 0 and 5 meters of depth. So even though all of them have good energy potential, not all of them can admit any kind of turbine. And what we did next was a bit of a comparison, because we wanted to see how do we stand with these 5 estuaries against other important places of hydrokinetic energy in the rest of the world. So we thought, okay, maybe we can do this with an index. And we did a little bit of research to see what was available to do this comparison. And we found several, but here I'm showing you just 3 indexes that seemed both useful, but at the same time very different to compare. As you can see here, there are the main variables that are involved, and in all 3 cases they are similar, but the way each index calculates them is actually different. So the results we'll see next vary a lot. And for these 2, the objective is to surpass a value of 1 to determine if the resource is exploitable. And in this one here, there's no threshold, but there's a ranking that has been made for the sites in the USA, the best sites for hydrokinetic energy in the USA. So we couldn't decide which one was best, so we calculated all 3 for all 5 estuaries. Here you can see just 2 examples for Santa Cruz and Gallegos again. This is the TSE, this one here is the IHE, and this one is the NRL. And you can see, for example, if you compare these, same happens here, there's a very different distribution of the optimal areas for exploitability. And even here, for example, you see this blue line. This is actually a navigational channel that this is the only index that considers that kind of interferences. So again, we calculated all this for all the 5 estuaries, and we couldn't decide which one was best. So we thought, okay, they're all good for at least for something, which is what you can see here. If we put all this information into a table, you can see that there are large areas, depending on the index for each estuary, in which we see that we could eventually use them as hydrokinetic projects. For the first indicator, we've got only 3 estuaries. For the second one, all 5 of them could go, and for the third one, just 4 of them. But the important thing here is that all of this show that there's some kind of energy potential available for exploitation. And actually, if you compare the NRL scores obtained here against the ranking of the USA, they all 4 of these fall within the 36 best places for hydrokinetic energy. So this shows that maybe the resource is not the best in the world, but still is very important. It's very considerable. So we can keep on investigating because it's worth the while. Now, the thing is that we obtained this result that I was mentioning before, but how do we go from where we are now, just a resource assessment, up to a exploitability? There's a big gap to cover. So we thought, okay, how can we synthesize all the information of all the estuaries that we gathered? And we decided to do these 2 plots here, 2 histograms that show the area with mean current velocities above 1 meter per second in both cases, here as well, varying in depth and in mean power density for all 5 estuaries, as you can see in the colors here. And this allowed us for a very quick classification. If we match this information with the tidal turbines that are available currently or that are being developed, we can establish a threshold of 20 meters in depth to separate the small and medium scale devices from the large scale devices. And if we do that for a threshold of 1 kilowatt per square meter, we can separate the testing devices from the operational devices. So these are 4 categories that are very useful to assess the variety of uses that can have the same site. So if we gather all that information, we obtain these plots here that basically they show us in which areas we can have, for example, in gray we have the areas for small devices for testing purposes. In blue we've got the small devices for operational purposes. In orange we've got the large devices for testing purposes, and in green the large devices with operational purposes. So you can see here that they all have one or another area here. And we can also see the distribution in space, which is very handy for decision making. If we gather all this information into this table, an important conclusion that we can draw is that all 5 estuaries are suitable for small devices, both for testing and operational purposes, but only 2 admit large devices for testing purposes, and only other 2 large devices for operational purposes. And Santa Cruz here is the only one that actually admits all 4 of these categories. So this is actually a different approach that we decided to take, which is actually simpler, but still it's very handy to determine what to install and where, and the capabilities of each site can offer. So that's it. Thank you very much.
Thank you very much, Lucas. We may have time maybe for one question.
Thank you very much for your presentation. I was wondering if we, as an academic community, can have access to a data set. It is public and open to work in simulations and so forth?
Yes, it's not available yet, but we're building a web map with all this information to be available. But I mean, if you want any of this, I can just email it to you. There's no problem. Yeah.
Okay, thank you. I have another short question. Did you use some kind of robotics intervention for doing bathymetry of high resolutions, or you are using from the service?
No, only ADCP and Ecosonda. I'm not sure the word in English.
Ecosounder.
Ecosounder, yes, but nothing autonomous. We went there to manipulate the devices.
Thank you.
Thank you very much, Lucas. And